Increasing the temperature of a mixture by 10 degrees can double the rate of a chemical reaction. Understanding this sensitivity requires looking past the beaker and into the mechanics of individual molecules. This graphic shows the physical sequence of heat. Raising the temperature increases the average kinetic energy of the system. Molecules move faster, colliding more frequently and with higher impact energy. This mechanical process forms the basis of collision theory, the governing framework that dictates whether a molecular strike results in a chemical change. For a reaction to occur, molecules must meet two primary physical criteria. They must make physical contact, and they must strike with enough kinetic energy to break their existing chemical bonds. This diagram lists the complete requirements. Even a high-energy impact will fail unless the molecules collide in the correct spatial orientation. Because these conditions are so specific, the vast majority of collisions are unproductive. The overall reaction rate is determined exclusively by the frequency of effective collisions, where all three criteria are met. We can observe these failure states by mapping the geometry required for carbon monoxide to react with nitrogen dioxide. In this illustration, an ineffective collision shows the carbon atoms striking at an incorrect angle. They simply bounce off each other. But with a correct trajectory, the carbon hits the oxygen at the precise angle to capture it, completing the reaction. But geometry is only half the problem. If these same molecules drift together slowly, the impact lacks the force required to shatter the original nitrogen-oxygen bond. This graph represents that force requirement as an energy barrier. Activation energy, or EA, is the minimum kinetic hurdle reactants must overcome to reach the product state. When we combine the variables of orientation and energy, we can categorize every collision into distinct failure and success states. The diagnostic matrix shows that 3 out of 4 collision scenarios end in failure. Molecules either lack the energy to react or strike at an angle that prevents bond formation. Only one quadrant results in an effective collision. Heat serves to push a higher proportion of the molecular population into that effective bottom right quadrant. To understand a complete system, we must move from individual collisions to the macro statistics of trillions of molecules. Chemists use the Maxwell-Boltzmann distribution to map the varying levels of kinetic energy throughout a molecular population. This distribution curve maps the fraction of molecules on the y-axis against kinetic energy on the x-axis. At room temperature, the activation energy threshold sits far right. Only a tiny shaded tail possesses enough energy to cross that line and react. The question is how this entire population shifts when the temperature is raised to 800 Kelvin. As temperature increases, the curve flattens and its peak moves right, reflecting a broader range of speeds. Look at the shaded area past the activation energy threshold. The shifting curve significantly expands the fraction of molecules meeting the energy requirement. This explains the high sensitivity of reaction rates to heat. The shifting distribution exponentially increases the molecules capable of clearing the activation energy threshold. This statistical reality is expressed mathematically through the Arrhenius equation. The formula relates the rate constant K to the frequency of oriented collisions and an exponential term containing the activation energy and temperature. Because activation energy is tucked into an exponent, calculating it from raw laboratory data is difficult. Exponential curves do not allow for the direct extraction of hidden variables. To solve this, chemists take the natural logarithm of both sides of the equation. This operation reorganizes the variables into a linear format. The complex exponential relationship is converted into a straight line equation, y equals mx plus c. When plotted, the slope of this resulting line represents the negative activation energy divided by the gas constant. By transforming exponential data into a straight line, we can calculate the exact activation energy of a reaction simply by measuring the slope. We can apply this logic to a real-world case study. If we have the rate constants for a reaction at 2 different temperatures, we can determine the activation energy. Raw temperature and rate values do not form a straight line and cannot provide a slope. The data must pass through the pipeline shown here. We convert temperature into its inverse and calculate the natural log of the rate constants to generate linear graphing coordinates. Once transformed, these coordinates are plotted onto a grid to establish the slope. The gradient of this line is negative 22,316, representing the steepness of the energy relationship. By setting that gradient equal to the Arrhenius slope and solving for EA, we find an activation energy of 185 kilojoules per mole. Mathematical transformation bridges the gap between laboratory observations and the thermodynamic properties of the system. In many engineering contexts, full datasets are unavailable. When only 2 data points are known, we use a more direct method. The 2-temperature shortcut combined equation calculates reaction rates by comparing 2 specific states. Here, knowing the baseline rate and activation energy lets us isolate the variables and find the new rate constant at 350 Kelvin. This methodology provides a complete picture of how temperature dictates the speed of chemical change. This summary compares the systems. Higher temperatures increase collision frequency and stretch the Maxwell-Boltzmann curve. Crucially, the massive expansion of the molecular fraction past the activation energy line is what drives the exponential increase in reaction rate. Ultimately, every chaotic collision taking place inside a chemical beaker is entirely governed by the rigid, fundamental rules of molecular orientation and activation energy. Translating these statistical behaviors into logarithmic graphs allows us to isolate the specific energy barriers of a system, making the invisible speed of a reaction predictable and controllable.